And a few announcements. So today we will have the Q&A session at 2 p.m. So there'll be more opportunities for you to ask questions to the lecturers. And also, we plan to take the picture in the beginning of the Q&A. I'm talking to people in Trieste that can participate online. Okay, so let's start the fourth lecture of Roman.
All right, let's get started. So yesterday we concluded with the calculation of the bispectrum, which I'm gonna put here. So again, this is a leading order in perturbation theory. I'm not gonna rewrite the kernel F2. So what I want to do today is try to understand the hierarchy first of all the non-Gaussianity that gets generated. Okay, so we calculated explicitly the three-point function or the bispectrum, but as I argued yesterday, you generate all the higher order correlation functions, and let's try to understand what kind of scaling do we get. Okay, so we can see from here the bispectrum scales as the power spectrum square, okay, to leading order in perturbation theory. So that's the thing that got generated, okay, by nonlinear evolution. And the way schematically, the way we arrive at this, right? The bispectrum is the three-point function, so we have three of these guys, right? If all of them are linear, because the initial fluctuations are Gaussian, this is 0. So the leading term was 1 is second order. Sorry, 1 is second order, and the other guys are first order, okay? And then because this guy goes as delta 1 square, okay, then you got 4 delta 1s, and then that gives you a p square, okay? That's schematically how this arises, okay? So now let's think about higher order endpoint functions, connected ones, and see what scaling do we get, okay? So let's now consider T sub n to be the endpoint function connected, right? So there are n of these guys. Okay, so here we have the case n equals 3. Okay? So again, the way to make this guy connected, so there are many terms, okay? In the three-point function case, there are only one contribution, right? But in general, there will be many, okay? I'm gonna do the 4-point function later, you will see how. But one way you can get a non-zero answer will be, by analogy from here, you can see if I have something like this, I have n minus 1, like here. So in this case, n minus 1 is 2, which are linear, and one guy which is n minus 1th order, okay, which in this case will be 2. You can see that now, because this scales as delta 1 to the n plus 1, okay, this will be even numbers of delta 1s, right, which for a Gaussian field has a non-zero answer. And so this will give you a power spectrum to the n minus 1. Okay? And you can show that this is exactly what happens. So we are going to do the 4-point function in a second. And so to leading order in perturbation theory, what you generate is all the connected correlators at endpoint functions will scale as the 2-point function to the n minus 1. Okay? Now, if you think about this for a second, this scaling has the topology of a tree that you can make from n points. So let's start from the power spectrum. Okay, so if I'm doing the 2-point function, I have 2 points. How do I connect 2 points? You connect it with a single line. Okay? And so that means, in this pictorial way of representing things, the 2-point function is just a link between the 2 points. Okay? Gotta go from n equals 3. Now I have 3 points, right? Because we are doing the 3-point function. The lowest order way in which you can connect 3 points is through 2 links. Okay? And each link is a power spectrum. And this is saying the bispectrum scales as the power spectrum square. And now you can be a little bit more precise. If I want to write this precise expression, right, if each link counts for a power spectrum, this vertex is going to be the F2 kernel of K1, K2. So I can associate in these diagrams, each dot, each vertex has an F kernel whose order is how many links it has, okay, in this case 2. And remember, F1 is equal to 1. So you can think of this that there is an F1 here and F1 here. But remember, F1 is equal to 1, right? So here is also an F1 and F1, but these are 1s. So you can think of this, and its cyclic permutations will be, then I have the second order can be here, and the second order can be here. Right? So these are all the cyclic permutations that you can make over 3 that connects 3 points. Okay? Does that make sense? Okay? So in the case of n equals 3, there is only one topology that connects through a tree the 2 points. So let's go n equals 4. So now we are doing the trispectrum. So now I have 4 points. So let me draw the 4 points that way. So one way of making a connected diagram out of this with the minimum number of links is just doing this topology, which is called the star topology. And this guy will be now an F3 kernel here, right? And here I imagine I have momentum K1, so this is a power spectrum of K1, K2, this is power spectrum of K2, power spectrum of K3. Okay? And of course, all the cyclic permutations, which I'm not going to draw now, okay? There are 4 possibilities, with F3 being in each of the 4 points. But there is another tree topology that can connect 4 points, which is the following. This one. Okay? And this one now is a bit more interesting. So there is an F2 kernel here. There is another F2 kernel here. Okay? And now, if I get into this vertex with momentum, say K1, this will be, you can write all the momenta here. Let's do it this way. This is one possibility. So this is P of K1, P of K12. Remember, K12 is the sum of the 2 Ks. Okay, so you can see now the connected 4-point function of the trispectrum, right, will scale as power spectrum cubed, right? Because now I have 3 links. Okay, so this is saying the trispectrum scales as the power spectrum cube. Okay, and you can keep doing this for all higher order correlators, but I'll stop here. And so for that reason, this calculation, instead of talking about leading order perturbation theory, you can say, we say tree level. okay? Because it's the lowest way you can make a connected diagram as endpoints is by drawing a tree, okay, with no loops. Yeah? No, but you cannot make it connected. You cannot make it connected. Yeah, so he's saying, why here I'm not putting a delta 2, for example, right? It has to be a connected, right? Otherwise, it will be an unconnected diagram, which is already non-zero in a Gaussian field, as long as the total number of fields is even, right? So we are calculating non-Gaussianity, so we are calculating connected ones, okay? So if you have precisely, you know, any number of guys and you have another guy, this guy has to have enough delta 1s to connect, to make a connected endpoint function. Yeah. And the lowest, you know, the lowest ways in which you can connect is precisely by a tree. Okay. Any other questions? Okay. So now you can see that the next two leading order calculation will be adding one more link into these diagrams, and they will become a one-loop calculation. The next two leading order contributions will have yet another link. This will be a two-loop calculation, and so on. Okay, so it's too bad I erased. Well, I didn't erase. Today's a new day, so what I wrote yesterday for the, remember I have this thing for the bispectrum. Schematically, when I calculated, you probably have this in somewhere in your notes. We calculated the leading order skewness, and then we did the leading order bispectrum. But I also have the next two leading order contributions, which were all these guys that add to 6 powers of delta 1, right? And now we can do these guys and see what diagrams, what one-loop diagrams arise out of these expressions, okay? So the tree order is this guy, right? Which in that notation will be just delta 1, delta 2, delta 2, delta 1 square, right? This is second order, this is first order, first order. So now we are adding links to this, one link to that. So if I have this diagram and I add one link like this will be precisely the 2, 2, 2, right? Because each vertex now is an F2 kernel. So that diagram represents this guy. Does that make sense? Okay. Then I can add the link instead of adding it here. I can also add it here. Okay, so this will be a diagram that will look like this. Okay. So what is here? Now here I have 3. You can see now I have 3 guys here. So this is an F3, this is an F2, this one is an F1. So this is a 3-2-1 contribution like this. Okay. Then, if I add it here, it will be exactly the same diagram with a different cyclic permutation, right? Now I can also add it like this. I can make this guy have one link that comes back on itself. So I will have here 1, 2, and 3. Okay, so this is also an F3. This is an F2. So these guys together are the only 2 possible ways in you can make a 3-to-1 contribution. So this looks a bit funny, but this will be a momentum Q that comes back on itself. So this will be an F3 kernel. If this is, say, K1, it will be K1 Q minus Q. And you can see now there is a loop momentum that is being integrated over. Okay, so these diagrams are one loop. So here there will also be one, apart from the external K1s, K2, and K3, there will be a one loop Q integration that you are integrating over. And then finally, I can do the same. Let me do it here. I can add a similar guy like this to this guy over here. This is another topology. So now this guy now has four legs here. So this is an F4 kernel. And it's 411, which is exactly this guy. Okay? And so in this way, you can build all the one-loop diagrams for any endpoint correlation function. Okay? And you can actually translate for a given drawing, if you have enough patience, and you look at the number, the combinatorics and so on, you can get the coefficients and everything. And you can get the expressions for any n-loop diagram to any endpoint function. Okay? And so this will be the one-loop diagrams corresponding to the bispectrum, which will be the next to leading order correction to this. So as you can imagine, this can get very involved, okay? But so what we are going to do now that we know this technology, let's apply it to the power spectrum, because the power spectrum is the easiest thing, it's the two-point function. So far, we did only linear theory, so let's do the one-loop correction to that, okay? And tomorrow, I'll show you how well all these predictions work, okay? Today, it's just building intuition and try to understand how these calculations are done. Okay, so let's go back to the basics. Let's calculate the corrections to the power spectrum, okay? So again, schematically, while doing the two-point function, so let me do it two fields, okay? Let's just do it as if they were all at the same point, but just to do quick estimates. So again, what we do is we break this into delta 1 plus delta 2 plus delta 3 and so on. Okay, leading order is this. Then you can have something like this, and then you will have okay, so this is the linear power spectrum that we already discussed. It grows as growth factor square. This one vanishes for Gaussian initial conditions. Okay, because delta 2 scales as delta 1 squared. This is the primordial three-point function, which for a Gaussian field is 0. And these guys are the two contributions that scale as delta 1 to the 4th. So this is the one-loop diagrams. These are the one-loop diagrams, okay? So let's do the same thing. So this corresponds now, if I write it in terms of the power spectrum, the tree order for the power spectrum is what we discussed already, okay? And now we add these one-loop diagrams, okay? So the 2-2, you can see is adding a link that goes from here to here. So this will become this. Does that make sense? Okay? So you can imagine the external momentum is coming here, is K, and you break it into a K minus Q and a Q, and it exists again as K. Okay? And then I can do the same thing that I did over there. I can add a loop that looks like this. Here, I can also add it there, but it's the same topology, okay? So now, momentum here comes Q, K. This becomes a Q, okay? And this becomes a K. So this involves the F3 kernel, right? So this is this, and the linear kernel, right, which is 1. And this involves F2 here and F2 there. okay? So out of this now we can construct the expressions for these loop diagrams, okay? So let's look at this guy. So this guy is known as P22 for obvious reasons because it's the 2-2 contribution. This guy is known as the P13. So the P22 has is now a one loop diagram, so I have to integrate over this momentum Q. Okay? And it has a link, which is a linear power spectrum of K minus Q. Another power spectrum at Q. And now it has two F2 kernels, one here, one there. And the two momenta in the F2 kernels one is K minus Q, the other one is Q. Here is the same, okay? They enter with different, say if you draw it like this, here will be this and that, and then when it enters is the opposite signs, but you can show if you revert the two signs of the two momenta, the F2 kernel is the same, okay, as we wrote it yesterday. And now I had to square it. And now if you think about the combinatorics, right, if I have an F2 kernel on one side and an F2 kernel on the other side, right, I can connect them this way or I can connect it that way. So there is a factor of 2 coming from combinatorics. Huh? Now I'm going to do the other one. Wait. Say that again? The F3 kernel? Yes, we'll talk about that now. Let me do it. Yeah. So now let's do this one, right? The choke refuses to do P13. Okay. That's a bad sign. Okay. So you see now, from this vertex, I have the way I drew it. I could draw it the arrow the other way. Okay. You choose. Okay. It doesn't matter. It's the same thing. So you see the momentum Q in my drawing is exiting from here, then it's entering. Okay. And so this will have now F3 of say Q minus Q, and then K. Then one power spectrum is at Q, one power spectrum is at K, okay? And then you just have to count how many ways are of making this diagram. So now I'm gonna do it here. I have 3 links, and then I have 1 link here, right? Okay, and then remember I can draw this circle also here, so that gives me a factor of 2. And there are 3 guys that can connect with this, gives me a factor of 3, so 6. Okay? And you can have a lot of fun with this, I can assure you, okay? So you can do all the combinatorics, exercise, write the expressions for this, okay? All right, so those are the one loop diagrams for the power spectrum, okay? You can build the whole machinery out of these diagrams. But let's think about the basics, okay? Let's go back to basics. What are these nonlinear corrections doing to the linear power spectrum, okay? So let's go back. So let's now estimate. So the 3 order is here, is the linear spectrum. Yeah. Yeah, the powers of delta 1s, yes, but it's the same as the power of scale factors, yes. Yes, yes. You can see, yeah, I'm going to do that now. You will see how this mirrors. So here I was counting delta 1s, right? Right? Okay? And remember, delta 1 square eventually becomes the linear power spectrum. So you can think of counting now in terms of how many linear powers appear. okay? Because at the end, we are calculating statistics, so it makes more sense to count the expectation values of correlators, okay? And because it's a Gaussian field, the linear power spectrum is the governing quantity, okay? So to lead in order, the nonlinear power is the linear power, right? Now, if you do the counting here now, you see each one loop diagram has 2 powers now, okay? So the one loop now has 2 powers, but it also has one loop integration, right? So there is a D3Q, right? So in terms of scaling, we are looking at power k. In terms of dimensions, this goes like this. Do you guys agree? Yeah? Okay, is that clear? Good? Yeah, so now I'm counting, okay? Forget about the Fn kernels. Remember, they are dimensionless. They are ratios of k's. So in terms of dimensions, they count as 1, okay? They have no dimensions, right? So these guys, if you count the dimensions, they are two linear powers and a D3Q, okay? So this is being integrated over momentum. Same thing here, okay? So the counting will be 2 powers and a k cubed, okay? K is the external momentum, so this will scale dimensionally as the only thing you have in the problem, which is the external momentum k, right? So you see the one loop diagram is the 3 times the dimensionless power. Okay, remember the dimensionless power is k cubed p of k, right? Which is a physical thing that tells you how big the fluctuations are, okay? Now let's do 2 loop, okay? What are the 2 loop diagrams, okay? So let's draw very quickly. But you already know the answer, right? Because I'm adding one link, so I'm adding one p, and I'm adding one more loop integration, right? So the 2 loop will be p linear cubed and k to the 6th. So it's p linear times the dimensionless power squared. So each time I do one more loop, I'm adding 1 power of the dimensionless power, okay? And so that's telling me that this series is going to converge as long as this dimensionless power, which measures the amplitude of fluctuations at a given k, remember it's a physical thing, if this is smaller than 1, this is going to be a series that has a good chance of converging, okay? So this will be now, I can write it as p linear times 1 plus some numbers that will come out of this calculation, delta k, plus some number delta k squared, etc. Okay, and this is all dimensionless. All dimensionless. Okay, all the dimensions are in the statistic that you are calculating. Any questions about this? Sorry? Yeah, how many loops you have. So if I do now, if I add one more link, for example, I will have something like this. If I add it here, right, I can have something like this. Okay? I can have something like this. This is a bad boy. P15, horrible. So when we talk about divergences in a second, we'll have to deal with this guy. You can see now, these are the 2 loop diagrams, okay? And you can keep going, okay? You can do 3 loop, but each time I'm going to the next non-trivial order, I'm adding a k cube because I'm integrating over one more, arbitrary momentum, and I'm adding 1 power. So I'm adding k cube p of k, which is the dimensionless power. So this perturbative calculation can only have a chance of working if delta k is less than 1, right? Because each order you're doing is suppressed by the amplitude of fluctuations. And And so we usually define K nonlinear to be the scale at which the linear power, the linear fluctuations cross unity. So remember when we drew the linear power spectrum, I did this thing, right? And it goes as k to the minus 3 here, times some logarithms, which we'll talk about later. So k cubed p of k is some function that is increasing with k, right? So if I multiply by k cubed, this is p, this is now delta. Okay, it will be, forget about the VAO. Okay, so eventually, this will cross unity. This is what we call the nonlinear scale. And once you pass this nonlinear scale, this is going to be typically larger than this. This is going to be even larger. So you cannot truncate this series because you are leaving out things that are larger than the ones you included. No chance of working, okay? And the other thing you have to remember is the linear power is growing like the growth factor square. So when you are at high redshift, you are here. So the nonlinear scale is very far. So at high redshift, when the universe is more homogeneous, this will work a lot better. As you go to later and later times, this linear power is growing, and more modes cross the nonlinear scale, right? So at high redshift, you are somewhere here. The nonlinear scale is here. So the nonlinear modes are all from here to the right. At lower redshift, now you are from here to the right. And as this keeps growing, more and more modes go into the nonlinear regime, okay? And so the more you go into late times, the less number of modes will be able to be described perturbatively. There was a question over there, yeah. No, he was, sorry. Yes. They are what? Different nature from what? It's the same as the nonlinearities. Yes. So are you a quantum field guy? You sound like a quantum field guy. Okay. So here's the typical. I've taught this many times. That if you know too much quantum field theory, you get confused by this. Usually in quantum field theory, the loops have to do with quantum corrections. This is all classical, first step, right? H bar equal to 0 in everything I'm doing, okay? Okay, there is an H bar in the amplitude of the fluctuation power, the curvature perturbation that Gonzalo is gonna about. Forget about, yeah, I'm just taking that amplitude, okay? So, but in quantum field theory, the diagrams for the fields already have loops. My diagrams are all the F2 kernels, right, for the field. So if I do delta, right, it will be the F1 kernel, right, plus the F2 kernel, plus the F3 kernel. So they are all trees, right? This is the same as saying delta is the linear delta plus the second order. So no loops, they are all trees. It's only when I do the two-point function that I have to connect the links, and I will create eventually loops, right? So the loops are just, in this language, it's just the nonlinearities when you have, you go to higher order in perturbation theory, but has no quantum field theory here. So some of the techniques we are borrowing from quantum field theory, but yeah. Yeah, it's like a classical, field theory. So say if you go to StatMech, you can also have, diagrams and with, no quantum fluctuations. Same idea. It's a classical field theory. We borrow the same ideas, but yeah. Any other questions? Yeah. What is what? The K2, 3, you're saying? Yes. Yeah. Yeah, it's because, remember here, there is, maybe my notation, let's forget about this and put a D3Q here. Right? So dimensionally, this counts as 3 powers of K, right? So once you do the calculation, the only external Fourier vector that you have is K. Q is gone because you integrated over. So to respect the dimensions, if you did one loop integration, you get, for each loop, there is a K cube that enters. Okay? So that's why here it's 2 loops, it enters K to the 6. Okay? So this is all dimensional analysis. I'm not doing anything deeper than that. What is, yeah. Very good question, yes. This only tells you, doesn't tell you anything about non-Gaussianity because we are doing the power spectrum. It only tells you, you see now, very good question, right? Because you see the key is that this thing depends on K, right? So the shape of this guy will not be the shape of this guy. So it's changing the shape of your 2-point function. And because this is larger, the larger the K is, at low K, this goes to 0. So at low K, still the linear approximation works, right? So what will happen is that if I now draw in yellow the nonlinear power spectrum, this will not be changed, right? Depending on where, at what redshift I do this, then you will start to see changes here. Okay? Yeah. Very good question. I'm going to talk about it later. You have to do numerical simulations. Yeah, so I'm going to talk about simulations next. Okay?
No, you can go ahead.
Okay.
Oops, no, you cannot. No, you can.
But there's a topology problem here. Let's unlink. Let's put Genius back to 0. Okay. So, all right. Yeah, so very good question. That's what I'm doing next. The only way to check how far this works is to compare with something non-perturbative. The best way we have things to compare non-perturbatively is to do a numerical simulation. Okay? So now I briefly said that some of these loop corrections will be problematic, right? Because remember, we are integrating overall momenta here, right? And this, in principle, this integration is up to Q equals to infinity, right? I already told you that when you go to the nonlinear regime, this theory doesn't make sense. So you may question, wait a minute, now we are integrating over momenta here that the theory is not valid. So you have to question, are these integrations what we call UV sensitive? Okay, do they diverge? The answer, no. Okay, for this kind of spectrum, no. But they will be sensitive to the nonlinear regime. In particular, at this order, this one is very insensitive, but this one is a bit sensitive. Okay? So you don't have to do a renormalization in the sense that it will diverge, but you have to worry that you are integrating over momenta where this description is not quite right. Okay? So we'll come back to that later. And the more you have of these guys, I mentioned this guy is a bad boy, right? So this one will involve something like this. Now integrating over 2 loops, Q and P. This one will be is very UV sensitive, okay? So the more you go into more loops, this problem may become worse. All right, so let's talk about now numerical simulations. So what do numerical simulations do? Okay? And I'm sure you're going to hear a lot about numerical simulations from Paco next week, Villascusa Navarro. Paco, he's Paco. Don't need to spell more words than Paco. Um, but let me give you my take on it, okay, to make the connection with this and to address the problems of these UE sensitivities that may show up when you do these loops. Okay, so what do numerical simulations do? So remember how I started the discussion. I said I'm going to assume dark energy is a cosmological constant. Dark matter is cold and collisionless. Okay? So, simulations. What equations do simulations solve? As you may be aware, simulations, 99% of the simulations in cosmology, they treat dark matter as particles. Okay? Whereas the description we did here was a fluid, right? Perfect fluid with zero pressure. Okay? How do those two things relate to each other? Sounds like I sold you some dubious proposition there. So we have cold, collisionless, okay? Interacting only through gravity, okay? So these particles are not created nor destroyed, okay? So they obey an equation in phase space, which is the collisionless Boltzmann equation. So it will be a function of comoving coordinates x, momentum p, and then conformal time tau. So this is the phase space density. And because there are no collisions, this phase space density is conserved along the, is totally conserved. So the Blasov equation is, let me write the equation and then I'll explain. So let me write it this way. Because there is expansion of the universe, it appears, unlike a normal Boltzmann that you may have seen in StatMech. So this is, if you had collisions, there will be a non-zero right-hand side, okay? So P is the momentum per unit mass. I'm setting the mass of the particle to unity. And if you think about it, you can solve this very easily, at least formally. Yeah, let's erase very easy. It's not, nothing is easy, but you can find a formal solution, which is the interpretation that these are collisionless particles, by thinking, okay, I can think of this P over A as my dx dt. I can think of minus minus A grad phi, where grad phi is the gravitational potential that obeys Poisson equation. What is this? This equal to that, and this equal to that are the Hamilton's equations of motion, right? And so what this is saying is df dt plus dx dt df dx plus df dp dp dt. So this is the total derivative of the phase space distribution function is equal to 0. So this is saying the phase space density along the trajectories of the equations of these particles is conserved. Okay? Huh? The bar is a vector. So this one, no bar there. Yeah, thank you. Yeah. Okay? So this is saying, this is, if you have seen partial differential equations, which are like this is a method of characteristics, right? So you write the characteristic curves of the equation is along the direction where things propagate, okay? And so the Hamilton's equations of motion are the characteristics of the Blasov equation. Sorry, this is known. Blasov was the first to write this for collisionless long-range force with long-range force as gravity. So this is either Blasov or collisionless Boltzmann. So I'm going to use Blasov because it's shorter. It's like Paco. I don't want to say too many words. Okay? So, so this is saying the phase space distribution function is conserved along the trajectories of the particles. So then that gives you the interpretation of what a particle in a simulation is. A particle in an embodied simulation is not a dark matter particle, not even close. A particle in a cosmological simulation, if you're lucky, is 10 to the 8 solar masses. It's a huge thing, right? So what you are doing in a simulation is you are discretizing the initial phase space distribution function. So you should imagine that each particle in a simulation is a discretization of this at the initial conditions. And all the simulation is doing is saying f at a later time is the same f you have initially, where x is a function of the initial conditions, and p is a function of initial conditions. And these are the solutions of Hamilton's equations. So is this conservation statement, is this derivative equal to 0? So that's all the simulation is doing. It's taking this initial initial time. All the simulation is doing, particles are a representation of this. When you set particles in a grid and you do the initial conditions, you are generating this. And then you say this equal to that is the solution of that equation. And the way these guys are related are by solving Hamilton's equations of motion. Yeah, so these are coupled through, so let me write down now. So what we can now, as you usually do in particle mechanics, you can combine the two first-order Hamilton's equation into the Lagrange equations of motion. So that will be now for the trajectories, which are how it's done. Well, depending, yeah, there are some simulations that use Hamilton's, but you don't notice. So you can combine these two into the Hamilton's equations of motion. Okay, so it's a second order, of course, for the trajectories. Okay, and then, of course, the Poisson equation that we already wrote. Okay. So that's what the simulation is doing. Okay. Okay. All right. Now, how is this related to what we are doing here? How are these particles? So now I'm getting closer, right? I say these particles are actually a representation of this distribution function. Okay? So now things should start to feel a bit less dubious. How is the distribution function related to the density and velocity fields? Okay, so here's the relation. If I take, remember, this distribution function depends on coordinates and momenta, right? So if I integrate this over all momenta, I get my density. So I'm working in the units where the mean density is 1, okay, which you can always do. So the density will be 1 plus the density fluctuation, okay? So that means that one integration, so now this P is a momentum, okay? Nothing to do with the loops that I was doing here, okay? Okay, it's the momentum of the particles. Yes?
Is that an assumption?
No, this is truth. I mean, if you integrate overall momentum, the distribution function, you get the density. If you integrate, now if you multiply by P, so let me forget about the time. This gives you now the velocity times 1 plus delta, okay? And I'm suppressing all the arguments. Okay, so now you can see now I get a vector, and that defines the velocity field. So the velocity field is just the integral of this divided by 1 plus delta. So now, let's take the Blasov equation, integrate all over P, exercise, you get the continuity equation. Multiply by P, you get the Euler equation that we wrote earlier, but with a non-trivial right-hand side, because you see, each time I multiply by P, there is already one P here. So that's why in the continuity equation, you're writing the equation when you don't multiply by any P, this will be the derivative of the density, but this will involve now the velocity. And that's why in the continuity equation, the velocity appears. When I multiply by 1 power of P to get the equation for the velocity, I get 2 powers of P here, a new thing appears, which is the velocity dispersion tensor. So now it's a rank 2 tensor. And this, you can write, let me see, how am I going to write? Let's be consistent with my notes. Yeah, sorry, you have to multiply by P over A, okay? It's always P over A. I'm forgetting the A's. So you're getting, so if you do this, you're going to get 1 plus delta VI Vj plus what we now define is a new object. You can see now this is like the second moment is the disconnected first moment square, right? Plus a connected piece, which defines the dispersion tensor. Yeah. Because this is a density in phase space per unit for unit D3P, right? So if you imagine, okay, let me draw phase space here. So now this is phase space. Okay, so 6D phase space, right? If F is the density, so if now you have the particles here, having a particle here means a particle is at this location and is moving with this momentum, right? So now if I integrate over P, I'm just summing over, say, I'm summing over this, right? So I'm summing all the particles that are at this location that have any velocities. That's the density, right? Yeah. Okay, and then if you multiply by P, you're accounting for their momentum, which is velocity, right? You can think of this now as density at the particular location times P is the momentum, velocity times density, okay, or mass per unit volume, and so on. So when you multiply by 2, you will get a piece which is, the 2 velocities weighted by the density, right? Because this is essentially has units of density, okay? And then you get a piece which is the non-trivial piece that I want to get to. Here's the difference between that and what we were doing here. Here, we were doing a fluid, okay? When you have a fluid, if I look at this particular location, the fluid has a velocity that points in some definite direction, right? But now think about dark matter particles. When dark matter particles are traveling, they are collisionless, right? That's the assumption. Look at what happened here. When they cross, at that location in space, one particle is going this way, the other one is going that way. So a fluid is not enough to describe what's going on once the orbits of particles cross. Okay? So what we were doing here is we are moving or evolving this system, assuming that there is no crossing of orbits, okay, which happens at small scales eventually, right? So we are ignoring this guy, because this guy describes what happens now if I have crossing of orbits. I don't have a single value velocity field. One particle is going that way, the other particle is going that way, Okay? That cannot be described with a fluid unless you add a stress tensor or a velocity dispersion tensor. Okay? So that means when you take 1 power of p here and integrate over p, this term is going to give you a non-zero dispersion tensor, and your Euler equation now is going to have a non-zero divergence of this dispersion tensor. Okay? Okay, so let me now write the corrections to the assumptions we were making here. How does the Euler equation get modified? Okay, and then we'll go to galaxies. Sorry? Right, because if you are average over large scales, you have these structures here, until they actually go through each other. That will take a very, very long time, right? So the first thing that happens is locally things are moving, so they are crossing on small scales. Yeah, and you will see it from the differential equation in a second. So let me write now so once you take a momentum average of that, you get the Euler equation that I wrote the other day, yesterday, I think. So this is the equation that we have. So now I'm writing in index notation because I'm going to need a tensor here. And now the extra term that you get so this is the new term that happens, that comes from. So the Blasov equation actually is now leads to something more complicated than what we are assuming, okay? And the point is that you start the simulation with this equal to 0, right? Because when you start, the particles are not crossing. This is cold dark matter. This can also be generated by thermal effects in the early universe. If it's warm dark matter, this will be non-zero, for example. But for cold dark matter, this is 0 initially. But once particle cross, then this gets generated. Now you say, OK, I need an equation of motion for this guy, right? So let's multiply this by pi pj. Bad news, now you have 3 p's here. So that gets yet another object into the game, which is a third rank tensor, okay, of the distribution function, and so on. So this becomes an infinite hierarchy. Okay, equivalent to the Blasov equation. Okay, good. So in the notes, I actually write. I cannot go on with this because it will take a long time. But I actually describe a little bit more how this guy gets generated, okay, through orbit crossing and so on. So you can read that on your own. So in the last few years, what we have done is to actually solve this hierarchy. Okay, it's a mess. I'm not going to go through it here. But that, because now you have velocity dispersion, so the fact that this guy is non-zero actually decreases the UV sensitivity of all these loop diagrams. Okay, and they become very nice convergence properties at high Q, which will not be the case if you ignore this. Okay. The alternative, which has been very popular, is to actually model this in effective field theory. And effective field theory, what it does a gradient expansion of this guy, okay, with free parameters that then you fit to simulations or you fit to the data that you are assuming, okay? So in effective field theory, this is now treated. If I take, remember, we are taking the divergence of this equation to have the evolution for the velocity divergence. This will add now a term which will be another divergence. There are 2 derivatives here, and to 0th order, you can take this to be a constant. That's what effective field theory does to leading order. Okay? So this will give you now to leading order, again, delta is much smaller than 1, right? And then you get the Laplacian of delta times some constant. Okay, so that gives you a contribution which goes like this in the equation for the velocity divergence. Okay? And so in k space, this will just be a k square. This is some parameter, free parameter, that you will fit to simulations or to the data that you are analyzing. So it will be a k square delta with some coefficient here, which is free. Okay? And so in that case, the one loop power spectrum of EFT, one loop, are the one loop diagrams that we computed in SPT. So those one loop diagrams, okay? And now I have a minus k square delta. I correlate it with the linear delta and give him a minus k square p linear. Okay? Maybe with a factor of 2. Because there are two, there's a 2-point function, so there are 2 combinations. Okay, so another way of thinking about this is to say, well, this guy is UV sensitive, okay? And you can check what happens at high Q, right? And you can check that, remember, I told you that for total momentum K, when K is much smaller than these guys, this goes as K square. So at high Q, this goes as K square over Q square. And you can see it has a correction. So this is UV sensitive with the external momentum K square and some integral over Q, right? And you can absorb that UV sensitivity into the redefinition of this guy. Because this also goes as K square P, which you will have here, K square P of K, okay? So the UV sensitivity of this diagram can be absorbed into this free parameter that EFT has, okay? So I'm gonna talk more about effective field theory now for bias, but are there any questions about this? Yeah. Yeah, so if dark matter has interactions, then you have to tell me what they are, and they will be here. Yeah, if it couples to some other thing, yeah. Or there are collisions, or yeah.
I didn't understand where the first term comes from.
First step.
First term.
First term. This one? Well, this one is that calculation. Yeah. Because when this is 0, it reduces to that calculation. So then I'm including what is the non-trivial effect coming from this term. And to lowest order, I can take this to be some constant, which I call this gamma. Okay? And this will give you a term that this is this in the Euler equation. Yeah. So, you know, but what the simulation is doing is solving that hierarchy, okay? That's what the simulation is doing. What EFT is doing is modeling this in a phenomenological way, or basically is, you know, a gradient expansion, okay, and powers of k square. And to lead in order, that's all you need. You need this coefficient here, and you can fit that coefficient, okay? But the simulation is actually, of course, doing something, you know, more complicated, okay? And as I said, we now know how to solve this hierarchy also perturbatively. So we can include all the degrees of freedom in this. It's very complicated, but I'm not gonna get into that. But that also cures all the UV sensitivities of these diagrams in a more, but you have to make the assumption that it's really collisionless. The nice thing about EFT is not only it's valid for this, but it's valid for, because it's using only the symmetries, it's valid for all kinds of things. Whereas if you try to solve the hierarchy, of course you are assuming dark matter is collisionless, okay? Okay. Yeah, so when you run an n-body simulation, yes, I forgot to say, thank you. So the cosmological parameters enter, so you're going to get some initial perturbations, right? To set up this, you need to know what the linear power spectrum is. So you need to know this shape. That depends on cosmology. You are solving the Poisson equation, which depends on cosmology. And then you are solving for the background. The simulation is solving this equation through Hamilton's, or this equation, this Lagrange equation. And then it's also, of course, Robertson-Walker, all the equations that we talked about the first day, is solving simultaneously the background, how the universe is expanding and so on. Everything numerically. Okay, so now let's talk about galaxies, all right? So finally, now, in fact, I'm going to say, when I say galaxies, I mean any other, it could be some arbitrary tracer of the dark matter field. It doesn't have to be galaxies themselves. It could be, say, neutral hydrogen, like we do in Lyman alpha forest. You could be talking about, any other tracer, line intensity mapping, whatever. So when I say galaxy, I mean any. You take, there is dark matter, there are baryons, some things collapse, make some objects. You study those objects. How is that power spectrum and 3-point function or whatever related to the underlying ones, which is the matter ones that have all the cosmological information, okay? So that relationship between, say, I'm going to use G for galaxies. What is the relationship between matter fluctuations and, say, galaxy fluctuations, okay? So remember, the way we define density fluctuations, we say the density is the mean density 1 plus delta. Once we are talking about discrete objects like galaxies, we have typically a number density instead of a mass density. So it will be, again, mean density times the galaxy fluctuation. So that's the definition of delta G, okay? Now, clearly, there is not a one-to-one relationship to galaxies from dark matter, okay? Galaxies form from the collapse of baryons, right? And that collapse will happen preferentially inside virialized regions, which we call dark matter halos, where the dark matter virializes and is essentially in some sort of quasi-equilibrium. The baryons cool down, eventually collapse, they light up. We see the light as galaxies, and those guys form preferentially in high-density regions. So it's not these tracers, be galaxies or be hydrogen or whatever, they are not in a random sample of the dark matter, and so their clustering will differ from the underlying clustering of the matter, okay? And so the way we are going to do this, we are going to construct, again, an effective theory. So this is the most important application of effective theories in late-time cosmology, because it's very, very hard to predict from first principles what even innocent or nice-looking things as galaxies will be. I cannot predict from first principles what their clustering should look like. Even if I run a very expensive numerical simulation, it's very hard to do, okay? The greatest difficulties is that even the people that do numerical simulations of galaxies, where they put baryons and everything, they still don't agree on the physics, on the equations that you have to solve because galaxies are complicated. It involves star formation, it involves feedback effects, which is explosions of supernova, AGNs, and all kinds of, they have to put subgrid physics because you cannot resolve those ranges of scales, and there are many assumptions that go into this, and it's not clear what the right assumptions are. So apart from that, it's very costly. So when people run these hydro simulations, they cannot run cosmological volumes. because it's already very expensive. And different groups make somewhat different assumptions, and yeah, so it's very complicated. On top of that, there is the complication that observers don't care what the galaxy formation people are simulating, because they have to grab galaxies for a particular range of redshifts and given observational situations. So they do cuts in color, space, they do all kinds of, for observational reasons, okay? And that impacts, that impacts tremendously the kind of objects that you grab, right? And telling that to a simulator to, what are the conditions under which you select galaxies it's very, very even harder to implement in simulations, even if you had the right physics. As a story, sometimes I tell this story. Back in '94, I was a graduate student like many of you. I went to my first summer conference. I was starting thinking about galaxy clustering, how related to dark matter. And you see that if you use the symmetries like we're going to do now, lots of free parameters appear, which we call bias parameters. And I asked a famous simulator, which shall remain nameless, do we have a way of predicting this? He's a very well-known expert on simulating galaxies. And he said, in 3 years, I will give you all the bias parameters. So this was 31 years ago. I'm still waiting, okay? So this is hard, okay? Good. So how are we going to do this? We are going to take advantage that in perturbation theory, where perturbations are small on very large scales, we can actually use the symmetries that we expect galaxies to have, no matter, or any other tracer on very large scales, okay? And we are going to build an effective theory, which is all based on symmetries of what kind of relationship must happen between density perturbations and galaxy fluctuations, given some underlying principles, okay? So what are these underlying principles? Well, the first one, as I said, is that galaxies will form inside some virialized halos which have some scale, which we know, say for reference, this scale R star is, say, at most 1 megaparsec. Okay? So there is some locality to it, right? It cannot be that if something happens here, 100 megaparsecs away, a galaxy will form. Okay? There is not enough time to things to propagate that far. Okay? So essentially, when you are forming a galaxy, you are grabbing matter away from you at most from this distance. Okay? You're not grabbing things from much farther away. Okay? So we can consider, since we are interested on very large scales, where perturbation theory holds, scales much larger than, say, 10 megaparsecs, okay? Then we can assume that galaxy will be local. Galaxy formation will be local. So we are interested in such scales, locality. So we'll see later how we can actually relax this a little bit, okay? So that's the first assumption. Of course, the other important assumption is that structure forms mainly due to gravity. Okay? Gravity is the only long-range force which is not screened, so we can use to our advantage of the symmetries that gravity has. Yes?
I have a question. So to study these kind of things that are very nonlinear, you have to use those results that we found there? Because we already said that, for example, that series only converges if you are in the linear range.
Yeah, using EFT will not get around that. It doesn't get around the fact that you are doing a perturbative expansion. Yeah.
So you use those results.
Huh?
You use those results.
If you are calculating things analytically, you will either include this correction or solve the hierarchy perturbatively. But that's all you can do. And you will stop at some scale, which I'll show you tomorrow where you can stop, comparing to embodied simulations. Yeah. Well, because that's where the densities are higher, right? Yeah. So a halo has roughly, you can define it as essentially an object that is virialized and is roughly 200 times the mean density, okay, when you average over the whole size of the halo. And that's where baryons eventually cool in these potential wells. They collapse, and eventually you light up and create the light that we see. So. No, typically you will have the halo, and you will have a central galaxy, and then you will have little satellite galaxies, maybe, depending on the kind of galaxies that you're looking at. Huh? Huh? Yeah, this is all coming from simulations. Yeah, yeah. Okay, so what are the symmetries? So we are gonna, as I said, gravity is the dominant force at large scales. So we know that the objects that we have at hand are the velocities and the densities. So I'm going to assume, so I'm going to define, so now I'm going to I define my gravitational potential, right? I'm redefining it so that there is no coefficient here, okay? And you can do the same for the velocities. So you can have a velocity potential. Okay, so the Laplacian of the velocity potential is the divergence of the velocity field, which is this theta that we are using now. Okay? And so you can argue then that the bias relation, so this relationship is called bias, sorry. The bias relation should depend on these potentials, okay? Now, what are the symmetries that we have in the problem? We have the equivalence principle coming from gravity, and we have Galilean invariance. So the equivalence principle says that the gravitational potential can only appear at most, it has to appear at least with two derivatives. And Galilean invariance says the same for the velocity potential. So in order to respect these symmetries, we are going to assume that in this relationship, the only thing that can appear is you have to have operators which are at least two derivatives on these potentials, okay? Now, these guys are just, it has two indices, so it's a rank 2 tensor, right? But the density, these guys are scalars, right? So now we have to form all the scalars that we can construct out of these guys, okay? Also remember, in linear theory, these guys are equal up to the Hubble constant, which I'm ignoring in these arguments. So in linear theory, as we discussed, again, assuming the linear growing mode and so on, these two potentials are the same. So how many scalars can we build out of this? The obvious first scalar that you can build is just take the trace, right? So the trace of this is the density perturbation, the trace of this. So that's one way we can make a scalar. That's the lowest order way in which, or the simplest way in which we can make a scalar. How many scalars can we make out of these guys, okay? So this is a rank 2 tensor in 3 dimensions. There is a famous theorem that you may know from linear algebra that says out of a 3x3 matrix, you can only make 3 rotational invariants or 3 scalars. And those scalars in the physics literature are known as the Galileons. So the first one, the first Galileon G1 that you can make out of second derivatives of phi is precisely the trace. The second scalar that you can make, let's call it G2, is now take this, square it, and for purposes that will be clear later, we can subtract the square of the first. So that's another scalar. But notice this guy is linear in the potential. This guy now is quadratic. Okay? And the last guy you can make, as you might imagine, is the cubic Galilean, or G3. So let me write the definition. This is a bit of a, so ij, jk, repeated indices are being summed over, as usual. Singularity crossing the blackboards. And then finally, almost there. Okay, so you see here, my indices are right. ij, jk, ki. So that's a scalar, right? And the rest of the terms are combinations of the previous two, okay? In order to make some nice properties, so the nice properties is the expectation value of G2 is 0. The expectation value of G3 is equal to 0 as well. Remember, we were building fields which have 0 expectation value because they are fluctuations, okay? So that's a nice property to have. Now, this guy, you already know this guy by another name. Can you guess? This is the determinant of this matrix. Okay? This guy is the trace. This guy, as far as I know, doesn't have any name. But if you ever find a name for this, let me know. I've been searching, but I don't see any name. Mathematicians missed this one. Okay. All right? And if you try to build anything, any other scalar from this up to any higher powers, they will be combinations of this. This is the famous Cayley-Hamilton theorem that shows if you build a characteristic polynomial of a matrix, that characteristic polynomial evaluated at the matrix has to vanish, and that gives you a recursion relation from higher powers of the matrix to lower powers. We are in 3 because we are in 3 dimensions. If you are in 4 dimensions, if you look at the literature, the particle physics literature, there is a 4th one, okay, when you are in Lorentz case. All right? Good. I'm going really slow compared to what I wanted to be by the end of Thursday. Okay, so let's see. So we are going to build our basis of operators out of these guys. Okay, so let me tell you, since I have 5 minutes, let me tell you the result. Okay, you can read my notes. There is a lot of detail there. And it's, as you can imagine, it gets pretty complicated. But the main idea, it will be pretty easy, I think. Once you buy that I can do it from these symmetries, it has to be these guys alone. And the key is, in principle, you can have Galileos of phi, Galileos of phi v, but remember, to linear theory, they are the same. Okay? Now, I'm gonna write down eventually the one-loop power spectrum for galaxies. Remember, we had to go to 3rd order. Okay? So I'm gonna need to go to 3rd order. So this guy is cubic, so I'm gonna need to disorder in Galileans, right? But to disorder, if I do it for phi or phi v, the difference between velocity and density potentials is irrelevant because we'll be of 4th order in perturbation theory. Because to linear order, they are the same, and this is already cubic. I cannot see the difference, okay? So that simplifies my life. In the notes, I go up to 4th order, so you can even do the one-loop bispectrum if you wanted to, okay? But here, I'm gonna keep it simple. Okay, so essentially, these guys are sensitive to the tidal field, right? That, remember, appears in the F2 kernel and so on. So we are also, physically, we are including the tidal effects, okay, in the relationship between galaxies and dark matter. Okay, so that tells you that depending on what the tidal field is in some location, then the way galaxies form may be different, and so on. So that's the interesting thing. So you can write these guys as kernels as well, like the F2 kernel and so on in Fourier space. All the expressions are in the notes, so I'm not going to do it. But let's try now to build this relationship, right? So to first order, meaning linear in the field, the only thing I can do is this guy, right, which is linear in fluctuations, right? So let's do one, first order. There is only one operator that can enter the relationship. So this guy, so that means that gives me what we call linear bias. So if I only keep my relationship to linear ordering fluctuations, the only thing that it can be is some free coefficient, which we call the linear bias B1, that relates density perturbations to galaxy fluctuations. So to linear order is very simple. All we do is multiply everything we have done, but powers of B1, depending on how many deltas we have. Single free parameter, the only thing we can write. To second order, right? Then I can do the square of this, right? G1 square, which is delta square. So now I have to add here delta square, and the coefficient is called B2/2. Sorry for the factor of 2. Not my fault. And then we can do this guy, G2. So that comes with this coefficient. And these are the only two guys that we can build at quadratic order. So you see what we are doing? We are building this as a general effective theory depending on the underlying degrees of freedom that we have from densities and velocities, respecting the symmetries with free coefficients. Okay? One more order, okay? Then, of course, we have G1 cube. Again, don't blame me for the coefficients, but this Taylor expansion, this is some sort of Taylor expansion, historical reasons. I can do G1, G2, which is also cubic, and then I can do G3. Okay, so let's see. So this is just delta times G2. Delta times G2, the coefficient here is called, what am I calling it? I think it's gamma 2 cross. Cross because there is a multiplication by delta from this guy. And then the next one is gamma 3 G3. Okay? Now that seems, if the only thing you have is local in second derivatives, you have your, I'm not going to keep going. The notes go one more order, okay? Now here is an interesting thing, okay? That another operator that I can build to third order is to take the difference between G2 from phi minus G2 from phi v. Because the difference between this and this appears when I consider quadratic corrections to these guys. That will be a cubic operator, okay? So there is one more operator here, and that appears only because of gravitational evolution, okay, from what we talked about yesterday, that as you evolve the kernels, the nonlinearities make this guy different from that guy, or, which is the same to say, this guy different from that guy, even at the fastest growing mode, okay? And that operator you can show, you can write as a Galilean of two different scalars now, which is doing, so this guy now is sigma ij, sorry, derivative ij of phi 2 times derivative ij of phi 1 minus the Laplacians. And this obeys some Poisson equation. Okay, and that's not degenerate with this because to solve the Poisson equation, you have to invert the Laplacian, which is non-local. You have to do some integral with the Poisson kernel. So that becomes, that's called gamma 2, 1 times G2 now of these two fields. Okay, so the details about this are in the notes. Okay, so, and you can show that this is complete to third order. There is nothing more. Okay? So then, all you have to do now is to calculate, if you want to calculate the power spectrum, now you do the two-point function of this, and you will have all those free parameters appear. Okay? So what I'm going to talk about yesterday, I'm going back in time because I need more time. I wish I can go back to yesterday. Then I will, yeah. What I'm going to show yesterday is that these guys, when you do the one-loop power spectrum, these guys actually will disappear. They will become redundant with this. This is so-called renormalization. So we're going to talk about a little bit about that. And so essentially, at the end of the day, we are going to have 1, 2, 3, 4 parameters, 4 free parameters to describe the one-loop power spectrum. Okay? All right, so I'm going to, time is, yeah, so I wish I could go back in time, but yeah, let's stop here. And tomorrow I will use this bias relation to construct the bispectrum to 3 level for galaxies and the power spectrum of galaxies to 1 loop. And then we'll talk about redshift distortions.
So more questions for Ramon? Yes.
Hi. When we work with cosmological simulations, we can define gravitationally linked objects by over-dense region, okay?
By what?
Over-dense region.
Yes.
My question is, we can do it by physical principles too, or no, not?
No, because typically yeah, okay, it depends what simulations you are doing. If you are doing dark matter simulations, we know it obeys, if it's collision, it obeys the Blasov equation, and so we solve those equations, right?
Okay.
If you are talking now, putting baryons and everything, there will be free parameters. So that's what I was discussing in the answer to his question, that there is some scales that people cannot resolve, where stars form and so on, right? It's way too small to, so they do some subgrid physics with some free parameters, right? So when they actually do simulations of galaxies, there are free parameters which are tuned to observations. Okay, so even when you do simulations of galaxies where there are baryons and they are collapsing, they are emitting light and all these things, there are free parameters there, yeah.
Okay.
But if it's dark matter only, there are no free parameters. Only the way you solve the equations, there may be some.
But to define if in some region there is
a dark matter halo.
Yes.
Yeah, so what people do, so yeah, maybe Paco will talk about this next week. Some things that people do is take a dark matter simulation only, identify these virialized regions, say you run a halo finder, okay, with some prescription. You find a dark matter halo, and then you put galaxies by hand with some occupation distribution depending on what the mass of the halo is. There is some prescription for how you populate with galaxies, which will be some.
But by first principles, no. Okay.
I told you this story about this guy 30 years ago. He told me that he will give me the answer 3 years later, and I'm still waiting. Yeah, no, not yet.
Okay, I don't see any more hands. We have the discussion session And then maybe you can even advance some. Okay.
Yeah, maybe.
So let's thank. So we have a break.